Well, first of all, I'll update you guys a bit about the prototype. It's been out there for 4 years now off the coast of Portugal. It carries a 2 megawatt Vestas turbine, and it's produced 16 gigawatt hours as of last year. I was part of that team, or last month, sorry. I was part of that team in Portugal, and we learned a lot, and the learnings from this project will be applied to the future projects. Here's a video of the WindFloat prototype. As you can see, the air gap here is 10 meters, and we have a large, here's a WindFloat with the long swell wave coming in. This has a significant wave height of about 18 meters, and there's a model test that's similar, and you can see that the waves crashing in. You can see a lot of marine growth on there too. In this one, it's a much shorter wave, and but has a much lower wave height of about 8 meters. But you can see that the water did get on deck. This is because of the short waves, and the platform is much stiffer in this case. All right. So the next project that we are working on is the WindFloat Pacific project. It's sponsored by DOE, and we've just finished the budget period 2 of this project. It's a proposed 24 megawatt farm, which consists of 3 8 megawatt turbines. The plan is to fabricate off-site around Oregon, shipyards around Oregon, and then tow it south to the Coos Bay. So when the prototype was designed, we didn't really have a specific guideline to follow at that time. The ABS didn't have the offshore floating wind turbine installation guide. Instead, we used the mobile offshore drilling units guidelines, and really that just covered stability. So we kind of just used common knowledge, common sense, and kind of looked at WindFloat specific design, WindFloat specific components, and kind of just looked at what we would think were important to design. WindFloat specific components such as active ballast, the control system, the mooring system, and the specific turbine that you use. So I want to explain the active ballast system is a closed-loop system that shifts water from column to column to compensate for the wind load that we would get from the turbine at rated wind speed, to the maximum wind moment that we would get. So for example, if we had wind coming from a 0-degree heading from the south in this drawing, we would put half of the active ballast in columns 2 and 3 to compensate for that wind load, and we would be at even keel. So in the design process, we start with the preliminary sizing. It's pretty basic. It can be something done on an Excel spreadsheet even, where we just kind of decide, using our experience, what should be the critical dimensions, such as column diameters and lengths of the triangular structure. Then we take those numbers into stability analysis and make sure that those numbers that we've chosen works out. And then we do the load cases as prescribed by ABS, as well as additional cases that we may consider that the WindFloat may experience during regular operations, things that are important to us. And then we take the results of those load cases and we bring them into structural design, adjust accordingly, and then we do an iteration, making sure that all the changes we made still work and still apply. And we keep going until we reach a final design that we're happy with. So the stability criteria in ABS is shown here. It's a comparison of the stability curves. In those graphs, we have the heel angle versus the moment. There's the righting moment, which is the inherent moment. There's the restoring moment due to the inherent structure's geometry. And then we have the overturning moment, which is the environmental forces applied to it, either while parked or in production. Specifically for the WindFloat, we say that we don't want to operate, we have a maximum operating angle of roughly around 5 degrees. So if it ever exceeds 5 degrees, we would force a shutdown. Therefore, you can, in this case, you would see that there'll be an overturning moment for a production case up until 5 degrees, and then it'll drop off, and you get an overturning moment due to a parked case. There's different conditions. They include power production in rated wind speed and cutout wind speed. And then there's also parked at a 50-year storm or parked with a fault either on the RNA or the platform. An RNA fault would include a nacelle-yaw misalignment, whereas a platform fault we'd consider something like a ballast fault that would maybe create an undesired heel angle on the overall platform. Forgot to mention that. So when we do our stability analysis, we model in Rhino, and then we use an add-on called Orca 3D that helps us create these stability curves and other hydrostatic results. Another criteria that we have to do is look at the damage stability. One of them is to look at flooding in a specific compartment. The way that we do it is when we model it in Rhino, there's two ways to kind of simulate a flooded compartment. One way is to physically remove the compartment itself from the model, which would result in a loss of buoyancy in that section, which would equal a gain in weight, so that would be kind of simulating a flooded compartment by gaining the weight of the flooded water. Alternatively, we could use an intact structure and just modify the mass properties of it without adjusting the model itself. So we kind of alternate between the two methods and use whichever one is most practical for a certain given case. And then we get the resultant water lines, and we make sure that the damaged water line gives us a sufficient air gap. Here is some results from a stability curve. So we want to minimize as many, it's a simplified stability curve. We want to minimize as many cases as we can. So this WindFloat is symmetrical in 180 degrees. So that's the half of the cross-section of a triangle. And also you notice there's only 3 writing moments here because also it's a triangular structure, so at every 30, it's 60, and 120, you get some symmetry there. So the only 3 writing curves are needed. And then you can see the different overturning moments applied, either from a rated wind speed, power production case at a rated wind speed, which drops off at 5 degrees, into a much smaller overturning moment at the same wind speed, at cutout wind speed of power production overturning moment, which starts at a lower thrust but drops off to a higher overturning moment when it's parked, and then the 2 parked cases, parked at 50-year and parked with a yaw misalignment. You can see that most of them have equilibrium around 2 to 5 degrees, and our down flooding point is around 17 degrees, so there's a large range of stability there. And also we can calculate the overturning energy and compare it with the writing energy and ensure that we do pass the ABS criteria there. Next, we have the design load cases that are given by ABS. The strength load cases that we take the extreme of the cases and apply the load to the structure. For fatigue, we take a probabilistic model based on the site conditions, specific environmental conditions, and the directions, and we use a time series of the loads to calculate the fatigue. We use OrcaFlex and FAST as a coupled model for the hydro and aerodynamic and the control system of the turbine, and then we give the resulting loads into structure design through SAP or ANSYS. So the way that ABS has their guide, it's up to us to kind of interpret what certain cases mean. So when we look at power production faults, we kind of consider, hey, we want to operate at up to 5 degrees, but we don't want to consider any cases beyond that because it wouldn't make any sense. So we do a power production fault case at up to a mean heel angle of 5 degrees, and that's due to a controller fault onto the ballast system that would not right us back and bring us back to even keel. In a parked case, we can consider that the active ballast is bringing us all the way into the most unfavorable conditions, so that's roughly about a 10-degree heel, and we consider that with in the park condition during a 1-year storm. So those are some of those additional cases that we consider that are not explicitly mentioned in ABS. There's also some other cases that we want to not skip over, but we don't necessarily find to be driving, so we know that we can kind of put those aside and work on them later while we work harder to get better results for the driving design load cases. The way that we do the design load cases is that for the parked and production cases, we do 6 3-hour seeds of different waves. That's enough to get a sufficient a sufficient random wave. For events such as shutdowns and startups and other kind of wind-dominated events, we do 18 seeds of 10 minutes with different winds. One thing in the ABS guidelines is that there's 2 ways to consider wind and wave directionality. Either collinear wind and wave, they're both aligned and applied at the most probable direction, or wind and wave misaligned, but at various directions where they're most likely to be seen. The way that we do it, though, is a kind of conservative approach. We do an aligned wind and wave, and we do it for every heading. It just kind of simplifies our life a bit, and we find that it's a more conservative way to do it because most of the time you're going to get your extremes when both your wind and wave forces are aligned in the same direction. So this is the design load cases straight out of ABS that I mentioned. So when we do the design load cases, first for strength, we want to look at just the strength load cases. So denoted by the S or the F is the type of analysis, is strength or fatigue. Next, we have normal or abnormal safety factors. We want to find the cases with the most extreme in both normal and abnormal safety factors. The wind directionality, as I mentioned, we kind of ignore that column because we do a more conservative approach to it. So when we look at the design load cases, for example, the section 1 for all the power production cases, you can see that 1.3 to 1.6, they all are pretty much similar, except 1.3 and 1 to 5 have just different wind conditions, and 1.6 is in a severe sea state condition by the SSS on the waves. We've determined through sensitivities that the wind in this case is not really changing, is not really driving our design. It's not giving us extreme loads. In this case, it's actually when we're operating in the 1-year storm is where we see the biggest loads, the biggest motions, the biggest accelerations, and that's been proven through our models. So for the preliminary design, we focus on just the 1.6. We do the full analysis on 1.6. For power productions with the occurrence of faults, the way that we look at the fault is in 2.1 is a single system fault. So that means that in this case we have the occurrence of faults such as yaw runaway or blade pitch error on the blade pitch runaway on the turbine, or a ballast control system error. But we have a protection system that will lead to a shutdown, and therefore since we're shutting down, we don't really see the extremes in the initial moments of that fault. So we realize that 2.1 is not really significant compared to 2.2. 2.2 is the same thing as 2.1, except you assume that there's a fault in the protection system. So we continue to do the whole run with the fault kind of carrying through the whole system. And 2.3 is the same as 2.1 in our minds, except it's a different wind condition. So that also gets kind of lumped into the envelope of 2.2, where we just apply a single fault for the whole run. Next, we have the events, startups, normal shutdowns, and emergency shutdowns. So we want to focus again just on the strength load cases. In the normal startups, we do a maneuver called pre-ballasting, where we initially ballast the wind float in the direction opposite to where the wind thrust would be. So we would say, for example, if we were going to start up at a rated wind speed that would give us a heel of 10 degrees, we would first go and pre-ballast ourselves to -5 degrees, then turn on the turbine. That would bring us back to +5 degrees, and then the ballast system would operate as normal, and that would bring us to even keel. So since that startups are kind of controlled maneuver, we don't necessarily consider them for the initial analysis. The next ones are the normal shutdowns and the emergency shutdowns. We've done sensitivities, and we've actually determined that the normal shutdowns and emergency shutdowns do not actually differ that much when we look at the same conditions. So 4.3 is a shutdown during a 1-year storm, operating at your operational limit, and we also want to consider being able to shut down act as like an emergency shutdown, which is a faster shutdown. If we do see an oncoming storm, we want to have that option, so we kind of lump in the emergency shutdown into the 4.3 condition as well. And 4.2, we've also done sensitivities and noticed that they're not as significant as the 4.3. So next are the parked and parked with fault load cases. Again, we look at the strength load cases. 6.1 has always been a major driver. It's operating, or it's parked at a 50-year storm. It's in a very important case, and we do the full analysis on that all the time. 6.2 as well, it's one of the major drivers with the abnormal safety factor. It's the same 50-year storm condition, except there's a loss of electrical network. For us, we consider that to be a loss of electrical network on the RNA, which can lead to a nacelle yaw misalignment. So that's also an important case. 6.3, that's where it explicitly says it's an extreme yaw misalignment, but operating in a 1-year or parked in a 1-year storm instead. And we've seen that that is much less than 6.2 and 6.1, so it's not a case that we consider for initial design. For the 7.1 parked with faults, we consider that to be a parked case where we are heeling at the maximum of from the ballast system. So that's roughly around 10 degrees. That's also a very significant case for us, and so we always do that. So in summary, what we do is we start with preliminary design. We make sure that the structure initially works. We do as little load cases as we need to, based on the experience that we've done and have had in the past, to know that which ones really matter. We pass it through the strength. We pass the strength loads to the structural design team. Then we also calculate the damage and the fatigue life. And then we readjust the structure as we need to accommodate those stress loads or for increasing the fatigue life. And then when we have the structure that we're happy with, we run the remaining load cases that I skipped over, just to make sure that that everything I've done in the past is still true and that it passes the ABS compliance. That's it. Thanks for your attention. Well, it turns out for us that, at least for the site condition at the Pacific project off of Oregon, that we will operate up to 25 meters per second, which is the cutout for the wind turbine. That also corresponds to the wind speed, happens to correspond to the wind speed at the site for a 1-year storm. So that's how we kind of lump them together. And that's why it's not supposed to be a 1-year storm, it's supposed to be up to the cutout wind speed.
Yeah, I thought it's kind of, you go through the whole operating range, right?
Mm-hmm.
And then you pick a 50-year wave associated with every wind speed, right?
For that case, it's a 1-year wave.
It's 50.
Is it?
That drives our 1.6s.
To us, the SS
Yeah.
it means a severe sea state, which does not explicitly mean 50-year, but I'm not entirely sure. I think it doesn't. For us, we look at what we would get at the cutout wind speed, and use that wave height as the wave. Yeah. Roughly, that's due to the overturning moment due to the turbine. So in that case, for this specific structure, with a 8 megawatt turbine, we get 10-degree heel.
So how sensitive did you find the weight of the substructure to be with respect to healing?
The significance in that is the water plane area of the structure. So the diameter of those columns was a major factor in the how much you heal, the stiffness of the whole platform. Yes?
Is your design complete and now certified by ABS?
We have submitted a first pass, and I do not think that we've gotten the approval yet, but we have submitted a draft with our methodology. We haven't actually submitted a whole set of load cases to them, just discussing the significant ones that I mentioned here, and why we are not showing the results for the ones just yet.
And this was with an 8 megawatt?
Yes, correct.